Hello everyone, welcome to PrepTrain. Today we are going to discuss this part 2 of this paper, Apache Spark, a big data processing engine. If you are here for the first time, welcome. And if you are here after watching the previous video, the part 1 basically, welcome back. Till now we have discussed the introduction section, the page 1, page 2 of related work and Apache Spark, and page 3 of use cases and ecosystem. Today we are going to complete this research paper by going through the pending sections of architecture, multi-threading and concurrency, and Apache Spark use cases in some of the emerging technologies that are that have been discussed in this research paper. So without further ado, let's start the part 2 of Break the Tech with Saheb Kumar for Apache Spark, a big data processing engine. All right, till now we have covered the what and why of the Spark system, basically in the previous video. If you haven't watched it, do watch it. Like the earlier part of this research paper, I've already covered there. Today we are going to discuss the how part of the Spark ecosystem. When we talk about Spark architecture, the first line of this slide that is important. So a Spark application runs as a set of independent processes on a cluster, and this is basically the core concept of distributed computing. So what actually happens that you are not running a single program on a very big machine. What you are doing that you are running the entire program coordinated across different machines, and each of them are coordinating, and there can be again even 10 of machines, 100 of machines, or even thousands of machines depending upon how much data we are going to process and what is the capacity of each machine that we have. Okay, let's discuss the components one by one briefly, and then we'll go to the diagram. So the first of all, the first is driver program. This is like the master node. So it's the architecture is basically a master slave architecture. We will discuss it sometime in another video in detail maybe, or you can refer to other resources as well if you want to know more about this. So it is the brain of entire operation, the driver program basically, and it coordinates like centrally to every cluster that we have. And when you run basically a Spark submit command, this is where it starts. Secondly, we have cluster manager. So cluster manager role is a very different. It acts as a resource negotiator. So what happens, the driver program cannot allocate resource on itself. So basically cluster manager is asked by the driver program that, hey, can you please allocate me the resources, and then it evaluates how much it needs, and then depending upon how much resources we have, resources are granted to every kind of applications that needs to be run. Thirdly, we have worker nodes. These are the nodes where the actual work is being done, the data is being processed. Every node runs one or more than one executor processes, and the executor processes are basically like those hands which are actually doing the work of processing each of these data. So at a very high level, the process flow is something like this. There is a brain, let's say the driver program. Driver program asks the resource negotiator, which is the cluster manager, that, hey, I want to do this job. Then the resource negotiator, which is basically the cluster manager, it assigns some worker nodes to that task. Then the driver directly send those work to those nodes, basically the executors, and then that is being processed, and accordingly the user, whoever has run the program, they get the output. So at a high level, let me tell you what is happening. So there is this driver program, which is the brain of the entire system. Driver program is going to ask that, hey, the resource negotiator, which is the cluster manager, that, hey, I want to do these work. This is the level of data that needs to be processed. Cluster manager will assign some machines to directly the driver program, and then driver program will directly contact each of these clusters and tell them the work to be done. All right, this is a very simple diagram that has been given in this research paper. I have already shared the details with you about the research paper, and if you want the my personal copy for the channel supporters. They can get it via the link. I have already highlighted the important things over here. And apart from that, you can also get the PPT that I am using in this using the same link available for the channel supporters. So let's resume. And so this diagram that has been given in this research paper is pretty much simple. It's on the page 4 or the page 5. Yes, it's on page 5. And I have another diagram with me that I have made. So this diagram will help us understand the process better. So at the very top, we have the driver program. So driver program is basically where our code is living. So as you can see, the driver is the first and most important relationship with the cluster manager. And this driver program is only which communicates with the cluster manager. And uh, it tells the cluster manager that, hey, I need to run my job. Can you find me some place on the cluster? And accordingly, then cluster manager finds the resources, and then it passes on to the driver program like back here. And then eventually the driver program contact this cluster again. So the cluster manager then does its job. And in this diagram, I have put like 3 executor. So an executor is basically a dedicated process on a worker machine that exists only to run tasks for our specific application. Once the executors are up and running, the cluster manager main job is basically done. Then it breaks down it into a small tasks, as you can see. So the driver program send these tasks directly to the executors. So executor 1 is getting task 1, executor 2 is getting task 2, and likewise task 3. These executors are basically processors which are running the code for the piece of data that they have received. So they will run the code on only on that data that they have received for processing. And once they have processed it, this is entirely going in parallel. So this parallel execution of task, multiple executor will be working on, and this is what makes Spark so fast and scalable. So the executors basically then run the tasks and report it back to the driver. So all of them will then report it back here, and this is how it works. Okay, let's come back to the architecture page 4, and here we can discuss some more things that we can discuss in detail. Let's go into these components one by one. So first of all, cluster manager and driver, which is here on page 4 of this research paper that you can refer to. So let's first start with the driver program, because this is the brain part of Spark application. And this is where the main function of the entire application, where the first job will start running. It will go from here only. So the driver program is the process where the main function basically runs, and its job is to create the Spark context. Spark context is the basically object that represent your connection to the cluster. Once the Spark context is created, then it is the driver responsibility to get everything done for your application logic, like creating the list of all actions that are being done. Then it creates the DAG, the directed acyclic graph, like how these tasks will be processed. And eventually it is the orchestrator, basically conductor. So it decides which task needs to run in what order and on what data. And likewise, all of these things are being decided by the driver programmer. Now let's compare it with the cluster manager. So cluster manager is not part of your application. It's an external service, and it's standalone, and it is responsible for basically only one thing, that acquiring and allocating resources on the cluster. One interesting thing to know is the driver program is like a tenant on the system, and this cluster manager is like the landlord. So the driver program, if it comes and it says like, hey, I need 50 CPUs and 200 GB of RAM, then the landlord, which is basically the cluster manager, it will then look into the available resources and then it will allocate it. One more interesting thing to know is Spark is highly flexible with what kind of like the cluster manager you want to give. So it does not have its own cluster manager. It is like a plug and play system. So you need to assign which cluster manager you want to give. So basically the driver does not care that who the cluster manager is. Its task is to ask for the resource, and the manager job is to provide the resources. So it can be the standalone Spark manager which comes within the Spark ecosystem. We can use Hadoop Yarn, we can use Apache Mesos, and we can even use Kubernetes, which is being used in a lot of companies these days. Now let's break down the slave side of the architecture. So worker or executor, they might sound similar, but there is a fundamental difference between both of them. Firstly, the worker node. So this is simplest component to understand. It's just a machine in the cluster. So it's a server, a physical or virtual machine that has a CPU, memory, and disk. And its role is almost like entirely passively, just to whatever task is coming, just process using your resources. The active component on a worker node is actually the executor. The executor is basically a process which is launched on a worker node, especially for a Spark application. Now, when the cluster manager basically grants the driver the resource request, it launches these executor on the worker nodes. So these executors are dedicated to your application, and its lifetime also is attached to the same. The executor has primarily two jobs. The first one is, of course, to do the job that has been sent by the driver, and it executes the task. The driver sends it, and this is actually the number crunching. The driver says, like, let's say, the run this program for this partition of data, and the executor does it. Secondly, the executor is responsible for storing these data back to the partitions or on the disk, and if it is required to store them on cache, the executor then do that as well. Finally, executor is in constant communication with the driver. So once it finishes a task, what it does, it reports the result of that whatever the task, the data has come, it reported back to the driver program. And this flow that the driver program sends tasks to this executor, and this executor then reports it back to the driver program. This is the fundamental execution loop of any Spark job. Now let's come to the section E of the research paper, which is hardware requirements. This is on page 4 of the paper. You can refer it from the link or via Google search. So here basically we have already covered the software architecture of Spark, but now we are going to discuss the physical hardware part, because eventually these all software will run on a physical hardware only. And as engineers or architect, our design choices are always constrained by the these metals, the bare metal. So this is critical, because provisioning your clusters or correctly is a difference between a high performance system versus a very slow system. First of all, the storage system. So the paper that when I was going through it, so it notes that you need to keep your storage like HDFS very close to the compute nodes. This means that co-locating your data nodes and your Spark worker nodes on the same machine, or basically at the minimum on the via the same network, is better, because data locality, if it is there, then the speed will be faster. If a Spark executor can actually bypass the network part, because the data is on the same machine, so it will bypass the network entirely, which will be a important and massive performance win, because it will be faster. Next, local disks. So this is a common place to make a mistake, because you might think that Spark is in memory, so I don't need fast disks. That is completely wrong. Spark basically uses local disks heavily, especially for shuffling. So the process of redistributing the data between executors and operations like joins and aggregations. So these all things are there, and if that intermediate data does not fit in the RAM, then it will go into the disk. Talking about memory, this is one of the most important one. Spark basically lives on the RAM. So this more memory means more data can be cached and fewer spills to the disk, and likewise, and faster execution basically. So the key rule of thumb is basically to allocate at least or at most like around 75% to the memory to Spark, and leave the rest for the operating system and its buffer cache. The reason for this is, if you give 100% to Spark executor, then it will starve the OS for performance, and again it will lead to bottlenecks of poor performance basically. Network also cannot be neglected, because once the Spark application is running and the data is in memory, then the Spark application becomes network bound. So there are periodic shuffling required constantly, due to which executors needs to send data to each other. So a 10 gigabit or faster network might be a good option. Finally, the CPU cores. So Spark scales beautifully with the cores, because tasks are generally independent, but you can throw cores at the problem. And the recommendation is to basically start with at least 8 to 16 cores according to the research paper here. And this hardware blueprint, basically plentiful RAM, lots of local disk, many cores, this is the foundation for a very high performance Spark cluster. Let's talk about multi-threading and concurrency section, which is section F on the research paper, which is on page 4. So this is talking about a very important and nuanced topic, that multi-threading and parallelism in Spark. So as we have already discussed, so Spark gives the option of multiple languages, Scala, R, Python, Java, and likewise, but the most famous are mostly Python and Scala. Your choice between both of them isn't just a matter of preference. It is an architectural decision as well. Let me explain you why. So let's start with the Python disadvantages. So because there is a design feature called as global interpreter lock, or GIL. So GIL, you can read more about this. It does not support, basically the Python does not support true multi-threading for CPU bound tasks. So what happens that if there is a single Python process, what will happen actually, that only one thread will be executing the Python bytecode at any point of time. Now it can handle input output bound tasks in parallel, like waiting for the network request and all. But if your task is computationally heavy, like spinning up multiple threads in Python, it won't help to make it run faster. And this is a fundamental limitation of the C Python interpreter. Now look at the Scala advantage. So what actually happens is, Scala is just like Java. So it runs on the JVM, which is the Java virtual machine. So JVM, and this JVM has a mature, sophisticated OS level threading model. So it has full access to the JVM's multi-threading capabilities. And what happens that this means that a single Spark tasks, if that is written there and in Scala, it can spin up multiple threads like at the same time, and they will execute in like parallel on even different CPU cores. So if you have a very complex function that need to process a partition of data, then you can process it with Scala. But parallelizing that function within a single task, you cannot simply do it with the CPU bound work in Python. So based on the previous parallelism discussion, comparison between Scala and Python, who do you think is better? And even if you do think that like Python might be good or bad, so does it matter or not? So let's discuss that how does Spark actually achieves parallelism in practice. So this is a very interesting thing. So let's look at first the Spark parallelism model. So by default, Spark actually achieves its massive parallelism by running many single threaded tasks. So what actually happens, it does not rely on your code being multi-threaded. So it breaks your job into hundreds or thousands of small tasks, and then it runs each of those of task in its own thread or executor core. So this is a very coarse grained and highly scalable model. The task execution flow is basically controlled by the resources that you have allocated. So if you have let's say given 8 cores, it can run 8 tasks at the same time. So each of those 8 tasks will be running its in own thread. And what will happen, this is the primary way the Scala will scale, and it will work ideally for both like same for Python or Scala. So this parallelism comes from the running many tasks concurrently, not from running one task into many threads. We also have this concept of intra-task concurrency that I wanted to discuss. So this is where the language choice matters. Reason being, when a task itself is a typically single thread, so the code within that task for that task, it can be multi-threaded, especially if you are using Scala. This leads to like advanced Scala concurrency. So Scala integration with JVM can help us because with the JVM we aren't just limited to the raw and manual thread management that we have from the Spark. So Scala provides much more advanced and safer ways to basically handle the data. We are talking about here futures for non-blocking async operations or actors for message passing concurrency, and likewise. So this allows a Scala developer to build very sophisticated or highly concurrent logic inside a Spark task. So it can be a powerful tool for certain cases, or let's say certain complex problem. But in contrast to that, if we talk about Python or R, then we will see that they do not support true concurrency for CPU bound tasks. So what actually happens that it can lead to overhead in some specific like advanced use cases. We are finally in the last section, one of the last section, which is section G, Apache Spark in emerging technologies. And a technology true test is basically its relevance over time. So Spark isn't just a tool for a batch ETL or something. It eventually is becoming a foundational platform for today's most advanced emerging technologies that this research paper wanted to highlight. So first of all, the paper talks about fog and edge computing. This is basically there are multiple sensors. So let's say there are IoT sensors, and the idea is to process the data very much near to where it has been created rather than sending everything to a central cloud. And this requires very low latency parallel processing, for which Spark is very perfect. And this paper basically gives a very great example using Spark streaming, mlib, and Kafka together to form the base for a real-time financial fraud detection that we can use. We have discussed this in the past as well in this same video. Secondly, advanced machine learning. So this is arguably one of the Spark biggest impact area that if we talk about today. So Spark is a premier platform basically for distributed ML or MLib library, and it provides a very powerful scalable library of common algorithms. But it's not only limited to its own integrated library. You can integrate other libraries with that as well. There is a one reference of Xboot integration which allows the users to distributed fashion on a Spark cluster. You can actually run a popular gradient boosting algorithm. One of the most important thing is deep learning that the paper talks about at the end. So DL is basically a computationally massive and distributed process. Because the data set is so huge, Spark has become one of the easiest ways to manage this distribution. Framework and libraries have been built on top of Spark to bridge the gap of the DL. The paper has given several more example inside that you can go through, LFS, Kairos, and likewise. So finally, we are at the end, the conclusion section of the research paper. We covered a lot of concept in these two videos and this entire research paper. It was very fun. So let's just go through all of them in a very brief manner. So first of all, what we discussed. So we discussed that Spark is a very unified engine. It is a hybrid framework because it can handle both the batch and the stream processing very efficiently. When they discuss about the performance, so the major factor is the in-memory computation that we talked about using the RDD abstraction. You can do more research on RDD. There are books where you can go through them more, or you can go through internet as well to learn more about RDDs. It's very interesting topic. Thirdly, Spark is a very rich and flexible ecosystem. Reason being, it's more than an engine. So it has library for SQL, machine learning, streaming, and it provides a comprehensive basically platform for every kind of big data processing task. We discussed about the architecture. So it has a master slave architecture, and it can be deployed on the modern system of distributed clusters. We can deploy on them, and then we can integrate it with Kubernetes and other things as well to maintain these clusters. So it is very easy to work with. And eventually we just discussed about Spark use cases in the future, where it is being used and how it is helpful for the entire tech community and the data scientists. So that's a wrap from this video. It was really nice going through all the concepts of Apache Spark. We discussed them in detail, and I am going through multiple research papers right now, and very soon I'm going to make videos on them as well. You can check out the research paper yourself in your free time, and you can also have a look at the PPT that I will be sharing in the description. If you haven't done it yet, do subscribe to the channel, and I will be very soon bringing more fruitful contents on this channel. Excited to be here. See you in some other videos with some other Break the Tech series concept. And that is all. Saheb Kumar signing off. Goodbye.